Before I start, I would like just to apologize if my voice is not very clear. I caught the flu today, so please excuse my voice if this is something that's a little bit bothering. And we should be starting. I think we are just about the right time now. So, as you all know, the topic of this webinar is auditing SSL TLS security of HTTPS websites. This is a very, very important topic. And unfortunately, from my experience, not everyone has some deep knowledge about it, especially those who are in penetration testing and vulnerability assessment. They lack some adequate knowledge in this particular domain. And as we're gonna see, some people just assume seeing invalid certificate in the browser is enough to point out that the website has an issue. It goes much deeper than that. But since this is the first webinar I'm doing since I joined Axon Institute, and this is the first webinar under the series of what we call Navigating the Cyberland. Let me give you like a brief background of this series of what's gonna be exactly, what is our vision of it. So we wanted to make this series a monthly webinar, free of charge. Anyone can access it, anyone can join it, where we offer some value and some important principles, important techniques in cybersecurity. And each time it's a different topic. The topics are like they are not chained together, they are not linked together, meaning if you attend one webinar, you can skip the next one, or if you did not attend one, you can attend the next one. So they are not linked together. You will not miss anything if you do not attend one in between like a few sessions. So each webinar has its own topic, self-contained topic, and the topic would vary in cybersecurity. Sometimes it's a tool that we will discuss and we talk about and we experiment with. Sometimes it's like a topic or a methodology in penetration testing or vulnerability assessment. Sometimes it's a walkthrough and tutorial, like capture the flag style, like in a guided way, you can say. So each time it's gonna be a different topic. And we have come up with the time of making this webinar on the second Thursday of every month at almost 6 p.m. Beirut time, EET, Eastern European time. So the topic of today's webinar is gonna be auditing and assessing SSL and TLS. And I'm gonna go through different subtopics, and they are as follows. We're gonna start by looking at the history and the background of SSL and TLS protocols, the different versions of SSL. We hear about SSL version 2, SSL version 3, TLS version 1.1, and so on. So we're gonna go about the history of SSL and what each version has in terms of new capabilities and the new features, and what has changed from version to version, and how it was developed, by whom it was developed, and so on. Once we cover the basic historical background of SSL and TLS, we're gonna go into the vulnerabilities and attacks that those versions have. Sometimes you might do an SS scan and then you see something like a POODLE vulnerability or a drown vulnerability. What are these? What do they mean? What is the impact of those vulnerabilities? And what is the implications of those vulnerabilities if you find them on certain websites. So we're going to cover few of the major attacks against SSL and TLS. And then we're going to talk about cipher suites. Cipher suites are those combinations of encryption and hashing algorithms that are used inside SSL TLS protocols. Some ciphers are weak and bad, some are strong and important. So we're going to review what are the characteristics of these cipher suites and how to filter out the good from the bad and so on. Then we're going to jump into a very, very important topic here, which is SSL hijacking. What are the different ways of hijacking SSL, decrypting SSL? There is certificate forgery and there is SSL stripping. There are different tools for it. And what are the causes of SSL hijacking and what is the solution of solving SSL hijacking? So from here we jump into strict transport security, the HSTS is very important, another very important topic, and it was inspired by the SSL hijacking attack. So the HSTS was a solution to the hijacking attack, and then we're going to talk about the O-Saft tool. There are different tools for testing and assessing SSL and TLS protocols, and the O-Saft developed by the OWASP organization is considered one of the best. It's very deep tool, it's very comprehensive tool. So we're going to cover the different options of running this tool and how you can run it yourself against different websites, so you can assess the certificates, the protocols, and the ciphers. And then finally, we're going to talk about the guidelines when it comes to SSL and TLS, the guidelines developed by OWASP. So if you are doing a pen test according to the OWASP testing guide, there are different guidelines and the principles that you need to cover. So we're going to look into these. I hope within 2 hours we can cover all of these. Otherwise, we might skip some insignificant part here and there. Let me give you a little background about me, myself. I've been in cybersecurity for over 15 years as a consultant and trainer. I joined Axon this year, and I am the leader of Axon Cyber Academy. And within Axon Cyber Academy, or our Cyber Institute, we offer different courses and different training in cybersecurity, particularly in different tracks: the penetration testing track, the security operations and the defense track, as well as the incident response and forensic tracks. In addition, we do internship and also research and development. So when we look at the SSL and TLS, it was introduced as a way of providing privacy, confidentiality to the HTTP protocol, not only to the HTTP protocol, even to other services like POP3, as we're going to see in a while. But before SSL and TLS, when we look at the protocol stack, we find that we have the IP layer, the network layer, and then on top of it, we have the TCP layer, and that is like port 80. And then on top of it directly, we have the HTTP protocol running. And if you are sniffing HTTP traffic and Wireshark, this is what you're going to see. You're going to see the internet protocol, the TCP, and then below here is the application layer protocol, the HTTP, and you see it in a clear text. You see exactly what is inside, what's being transferred. SSL was introduced so that it encapsulates the HTTP and then it encrypts it within on top of TCP. So when you sniff the traffic, you're going to see the IP layer and then the TCP layer, and then directly on top of it, the transport layer security, TLS or SSL. And within this layer, you're gonna see some headers related to SSL, so SSL headers, and then encrypted, bunch of encrypted data, and that is the HTTP, but in encrypted way. So this is how it looks. So it works on top of the transport layer, but directly beneath the application layer. So it's more of a session layer protocol. Probably you have heard about something called PKI, Public Key Infrastructure. Public Key Infrastructure is conceptual framework. It's not a protocol. So every time you hear about PKI, do not think of a protocol. It is a conceptual theoretical framework. It's a general framework that has been implemented in different protocols, in SSL and TLS. Not only in SSL and TLS, but also in other protocols like IPsec that is used for VPN is also an implementation of PKI. And in SSL and TLS as an implementation to secure application layer protocols. So it can secure HTTP, it can secure POP3, it can secure IMAP, it can secure SMTP, and so on. The PKI framework was meant to provide few security controls, confidentiality, and that is by encrypting the network traffic. So there is some encryption, form of encryption using symmetric encryption of traffic, and it provides integrity of data by using a hashing algorithm, something like SHA-1 or SHA-2, and it provides authentication of the remote server. For example, you are accessing HTTP, and then you need to make sure that you are really talking to HTTP, and that's what we call authentication. So you want to authenticate the remote server, and the way this is done by using a digital signature and other algorithms. In addition, there is a way within the PKI framework of how to exchange the private keys or the symmetric keys. So we have also key exchange. We're gonna look at how those controls are implemented within SSL and TLS. But the point that I want you to take away from here is PKI is conceptual framework. SSL and TLS are implementation, practical implementation of that framework, and that's why we see versions of SSL and TLS, while PKI does not have like PKI version 1 or version 2. It's simply a conceptual framework. With SSL and TLS, we have different versions, and with every version, some features are added, some security enhancements are added to the protocol itself. When you are doing a penetration test or a vulnerability assessment, there should be a complete section for SSL and TLS auditing and assessment. Whether you are doing a network level assessment or you are doing application level assessment. So if you are doing a network and system assessment and you are trying to do port scanning and then vulnerability assessment of all the nodes in the network, you're going to encounter like Windows system, and on top of it there is IAS system, and then this IAS is listening on port 80 and on port 443. Once it's listening on 443, you need to continue your assessment of the SSL protocol, of the SSL ciphers, of the SSL certificates, and so on. Additionally, if you are doing a web application pen test or VA that's running on top of the IAS, let's say it's a JSP application or PHP application or .NET application, and it's running on port 443 and it's using HTTPS, you also need to do an audit of the SSL. And as I said, the OWASP testing guide for the web application has dedicated section for SSL and TLS. And we're gonna look into that at the end. So when you are doing your assessment, it's not enough to report to your client that, hey, you have invalid certificate, self-signed certificate with this type of warning. You need to fix your certificate, and that's it. You need to dive deeper into why the SSL implementation is bad, the different vulnerabilities, the protocol, the cipher suites, in addition to the certificate itself, and if it is invalid, why it is invalid, what causes it, what is the impact of a self-signed certificate, and so on. So let's look at the history of SSL and TLS. It all started in the early 1990s when a company called Netscape Communications wanted to implement the PKI and develop protocol for its security. And those of you who are old enough, who can remember the late 90s, who have like worked in computers in the late 90s and early 2000, you probably remember the Netscape browser. And at that time, we had only Netscape and Internet Explorer before even the Google Chrome and the Firefox and all of these modern browsers. And Netscape was at war with Microsoft, sort of speak. So they developed this protocol privately, and they called it Secure Socket Layer, SSL. And the father of the SSL is called Tahir Al-Jamal. He was an Egyptian scientist at Netscape, and he was also a mathematician and cryptographer, and he developed this first protocol, SSL version 1. However, SSL version 1 was never released to the public, so it was internally used by Netscape. It has some bugs and some errors and some security issues, so they never released it. And then they developed SSL version 2 and they released it to the public in 1995. 1 year after that, they developed SSL version 3, which was like a complete rewrite of version 2, and they also released it to the public in 1996. In 1999, a non-profit organization called IETF, Internet Engineering Task Force, it is the same organization that has developed almost every open source TCP/IP protocols at every layer, from the HTTP to the DHCP to the ARP to the IP, TCP and UDP and so on. They took over this protocol, the SSL protocol. And what they did, they changed its name to Transport Layer Security for one particular reason, which is to save the face of Microsoft. They did not want to give extra credit to Netscape because Microsoft would be mad. So as a face-saving gesture, they changed the name so that the protocol would become neutral from Netscape. So it became the TLS protocol, and then they invented version 1, and then 1.1, 1.2, and the most recent one is the 1.3. So I said SSL version 1 was never released to the public. So what we know of is from SSL version 2. SSL version 2 was released in 1995, and it lasted until 2011 when it was deprecated. It has major issues in its initial handshake, the handshake that builds the SSL session, and it has an issue when you close the session. Both the initial handshake and closing or terminating the session was prone to forgery. An attacker can come as a man in the middle and start playing with the handshake or play with the end of data, and no one can detect, or there is no mechanism for detection, neither at the server level nor at the client level. So 1 year after that, they invented SSL version 2, released in 1995, but it deprecated in 2015. That's like 5 years ago. And it deprecated after a major attack or a major vulnerability has been discovered in SSL version 3 and that's called the POODLE vulnerability or the POODLE attack. We're going to look into POODLE in a while. It's a very major vulnerability that caused SSL version 3 to become totally insecure, and any hacker can decrypt a lot of sensitive data from it. So it became deprecated. But when it was initially designed, it was a complete redesign of SSL version 2, a complete redesign. And the SSL version 3, the way it operates is the basis of later TLS versions. So TLS Handshake and the way TLS communicate is majorly based on SSL version 3. And one of its features of SSL version 3 was the introduction of SHA-1, whereas version 2 has only MD5, version 3 has a mixture of MD5 and SHA-1. But as I said, a major flaw is its vulnerability to the POODLE attack discovered in 2014. Later on, the IETF came along in 1999 and invented the TLS version 1. They upgraded SSL version 3 to TLS version 1. And the two are not interoperable, meaning they cannot work together. So if a server and a client, one is SSL version 3, the other is TLS version 1, they cannot talk to each other. So both of them have to be TLS version 1 or SSL version 3. TLS version 1 has been deprecated last March 2020, along with TLS 1.1. And a major vulnerability in TLS version 1 is called the Beast attack. And we will talk about the Beast attack also in a while. And it's due to something we call implicit initialization vectors. All I want you to know here is initialization vectors are randomly generated sort of salt or a randomly generated block of data that is used to encrypt the plain text. And it's not randomly generated. It's not properly randomly generated in TLS version 1, and this is the basis of the Beast attack. I'm gonna move on now to version 1.1, defined in 2006 and deprecated also in 2020, in March 2020, just like 1.0. And a major update to the TLS 1.1 is the initialization vector here is randomly generated enough, and it's explicit as opposed to the implicit one. We're gonna see this in a demo in a while. But just keep this in mind that initialization vectors of the ciphers in 1.0 was not random enough, while in 1.1 it's random enough. However, another issue came with 1.1, and that is the crime attack due to compression. So 1.1 uses compression, meaning it tries to compress data to make the traffic, less traffic on the wire. But this compression, while it is a useful feature from the practical perspective, it can be vulnerable to an attack called the crime attack. And this crime attack is discovered in 2012. So in 1.2, 2 years after 1.1, that is in 2008, the version 1.2 was defined or was developed, and major updates to it are as follows. They added SHA-256, and they removed everything that has to do with MD5 hashing, and they also added a new cipher suite based on AES. We know that AES is enhanced version of symmetric encryption. It's much better and more secure than the DES or the triple DES. And the previous versions did not have AES. They used DES and triple DES, while the 1.2 has this AES encryption algorithm. Also, 1.2 added something we call TLS extensions. TLS extensions are extra features that add some enhancement to the communication. What are these features? There are plenty of features, but I'm going to talk about 3 of them that are like very commonly used. The first is called server name indication, SNI. SNI is a feature of TLS 1.2 and 1.3 that enables one server listening on HTTPS port, that is 443, to have multiple certificates for multiple websites. This is good in a shared hosting environment. So you have multiple websites of multiple domains, let's say axon.com domain, and I don't know, like another company's domain, all shared on the same server with the same 443 port. While you establish the TLS communication, the client can decide whether it's want to talk to the Axon website or to the other company's website, and then the server would respond with the appropriate certificate. This is done, or this is possible because of the feature we call server name indication. In a previous version, this was not possible. You cannot have 2 websites having valid SSL certificates at the same time on the same port. You would end up with one certificate for both or with invalid certificates. The other feature of the TLS extension is the elliptic curves capabilities. Elliptic curves, you might hear this term a lot, elliptic curves, especially in encryption algorithms and the cryptography and the key exchange algorithm. Elliptic curves are simply mathematical equations that are added to cryptographic algorithm to enhance performance, which means they can enhance the speed of the encryption process, or they can reduce the memory size. This is all they do. Okay, the details of which are completely mathematical, and I'm really not into the details of how elliptic curves work. All I know, they enhance the performance of cryptographic operations. A third extension that's also very important in TLS 1.2 is safe renegotiation. Renegotiation, as it is, was part of previous version of TLS, but had one major problem, which is it was done in a way that is insecure. A man-in-the-middle attacker can inject himself and issue some renegotiation statements, and the server has no way to know that the renegotiation attempts are really coming from the legitimate client. So in TLS 1.2, this was enhanced and this was fixed. So fake renegotiation attempts are detected and disabled directly. Sorry, insecure renegotiation was detected and disabled immediately, while secure renegotiation was allowed. And as it turns out, all this renegotiation stuff was considered at the end of the day bad, because they also had other implications. They might cause denial of service. So as we're gonna see in TLS 1.3, which is the latest one, renegotiation was dropped completely. No more renegotiation. Finally, 1.2 is also vulnerable to the crime attack, just like 1.1, which is related to compression. as we're gonna see in a while. Finally, the 1.3. 1.3 was defined 2 years ago in 2018, and some major updates are as follows. They dropped all support for MD5. There's no more MD5 in 1.3. They added, or they required, perfect forward secrecy, PFS. What is perfect forward secrecy? It was optional in previous versions. In 1.3, it is mandatory. Perfect forward secrecy is, in a simple term, is the following. If a hacker somehow, if a hacker by any means managed to get the session key of a secure communication, if he managed to reverse or get the key that the session is encrypted with, he can decrypt all communication and get access to all data. Perfect forward secrecy prevents this by changing the key at every certain period of time. So every half an hour, there is a new key. Every half an hour, new key, new key, new key, new key, new key. What this will do is, if a hacker can reverse or crack one key, he can only get access to a small portion of data instead of getting access to entire communication. So it will minimize the impact. And even modern applications like WhatsApp and Facebook and these kind of things, there is even a new encryption key with every new message. So that if a hacker can crack a key, he can only get access to one particular message, not to the entire messages or the entire communication. This is very important. So 1.3 requires perfect forward secrecy. All ciphers must have PFS. Also in 1.3, they dropped support for RC4. RC4 is also an outdated encryption algorithm. It's totally eliminated. They prevent something we called downgrading to SSL. In the previous version of TLS, like let's say 1.2 or 1.1, it was possible for an attacker to come in between and code the server to use older version of SSL. So the server support, let's say 1.2, but at the same time, it has SSL version 3 enabled or SSL version 2 enabled. A hacker can come and then forces the server to use SSL version 3 or SSL version 2. This is called downgrade attack. As TLS version 1.3 is immune to the downgrade attack. It's not possible anymore to downgrade a server to use a previous version of SSL. Also, the final thing, or one of the major update, is the handshake messages after the server hello. We're gonna look into what server hello in a while. The messages are encrypted. So only the first two packets or the first two stages of the handshake, which are the client hello and server hello, are clear text, and then the entire handshake after that is encrypted. While in the previous version, the entire handshake was not encrypted. So 1.3 currently, at the moment, is considered the most secure protocol when it comes to HTTPS. Let's look at the handshake. How does the handshake look like? When you first connect, let's say the server here this is Google, and this is your browser, Firefox or Chrome, and then you type google.com. What happens is your machine would do the three-way handshake, the typical three-way handshake, send, ACK, and ACK to port 443 at Google. Once the three-way handshake, this is not the TLS handshake, by the way, this is typical TCP handshake. Once this is done, your client will send something called client hello message. And then it will tell the server, I want to talk using this protocol, let's say TLS 1.2, 1.1, 1.3, and it gives it a list of supported ciphers. Ciphers are combinations of like packages of encryption algorithms and hashing algorithms that the client supports. So it will tell the server, hey, I support SHA-1, SHA-2, MD5, I support AES, DES, triple DES, RSA, all of that. And then it sent them with the client hello. Directly after the client hello, the server will respond with server hello, and it will give its certificate. And this is a very important piece of data that the client needs to have. So the server certificate will be pushed to the client along with the chosen cipher. So the client has given different options, what it supports. The server will pick the strongest one that it supports, and we will tell it, okay, let's communicate over this particular cipher, and here is my certificate, and then it will send server hello done. Okay, I'm done now with my hello. Okay, now you can evaluate your options, you can evaluate the certificate, and tell me if you want to continue the handshake. The client now would do very important step. It will verify the certificate, and the verification of the certificate happens through checking its expiration date, number one. It happens also through checking if it is signed, if it is self-signed or signed by a CA, which is the authority that issues the certificate, and it will check the entire chain. If it is signed by CA, it will check the whole chain. If the certificate is valid, it will send client finished. Okay, I accept the cipher, certificate is valid, let's talk. And then the server would send server finished, and then everything after this point will be encrypted. In TLS version 2, even a client finished is encrypted, while in TLS 1.3, client finished and server finished are encrypted. But in TLS version 2 and before, these are not encrypted. Only after server finished, the encrypted data stream take place. So, however, if the certificate is invalid, what would the client do? The client will give a warning to the user. The typical warning we're all aware of, like this site is insecure, it uses invalid certificate. Do you want to accept the risk? You say yes, accept the risk, accept the certificate. And then once you accept, client finished is sent. If you say no, then the TCP session is terminated. Okay, let's get into the major attacks and the major vulnerabilities that happen in SSL, different SSL protocols and the TLS protocols. The first one we will look at is called the beast attack. The beast attack, it's a vulnerability and an attack at the same time. The beast vulnerability or the beast attack. It was discovered in 2011 and is given a particular CVE. It's acronym for Browser Exploit Against SSLTLS, Browser Exploit, which means it's the attack. In order to succeed, the hacker has to control somehow the browser. Not only he has to be man in the middle, but also to do something on the browser through JavaScript or a Java applet. And as I said before, if you remember, it was due to initialization vector not being random enough or implicit. In a specific type of encryption algorithm, such as DES or triple DES, that are used in in a certain mode we call cipher blockchaining, the CBC mode. We will look into that. This attack is a form of chosen plain text attack. In encryption or cryptography, there are different types of attack to attack the encryption or the algorithm of encryption. And one of those attacks is the chosen plain text attack. In a very, very simple term, a chosen plain text attack is where I bring my own statement that's in plain text and I trick the victim to encrypt it with its own key or a system, and then I see the output of it. So let's say you encrypt your own document with your own key, and then I give you my own document and I tell you please encrypt it using your own system, and once you encrypt it, I take back the encrypted version, and now I have my plain text as well as the encrypted version using your own system or your own key. And from these two documents now, the original one and the encrypted one, I can do some analysis so that I break your own encryption. So the beast vulnerability or the beast attack is a form of chosen plain text attack, and it affects SSL version 2, SSL version 3, and TLS version 1. And it is fixed in 1.1 and 1.2 and of course 1.3. So we said it's part, or it is a form of chosen plain text attack, and it's due to improper initialization vector. Let's look at how it works from like crypto analysis perspective. Look at this image here. In this image, we have a document that needs to be encrypted. And if we choose an encryption algorithm like DES, triple DES, or even AES, the document is going to be divided into chunks, and we call these chunks blocks. Okay, we call them blocks. And then each block is encrypted by itself. So you can imagine the first block is encrypted, second block is encrypted, and so on. However, if you encrypt the blocks by themselves, what would happen? Let's say there is a word that takes an entire block. Let's say there is a word, something like hello, okay? The word hello. And if the word hello happens to be in the fourth block, for example, and encrypted by itself, the output of it is always going to be the same if encrypted with the same key, right? This means if I have, like, if you have a bunch of documents and all encrypted with the same key, wherever there is hello in any of these documents, it's gonna look like the same in every output. So what they do with a block algorithm, they chain the blocks, which means every block before it gets encrypted, it is XORed with the previous one and then encrypted. And this way, if there is a word hello somewhere in the middle, it's not gonna look like the same in the output every time, because every block now depends on the previous block. What about the first block? The first block is always chained with a randomly generated block we call the initialization vector, and that is the red block over here. Now, this is all good if we are talking about a single document. But when it comes to SSL, we know that the encrypted data are sent over packets, each on its own packet. So we have packet 1, packet 2, packet 3, okay? Now, in this version, in the beast attack and the beast vulnerability, only the first packet, the first block of the first packet is changed with an IV. But the first block of the second packet is not changed, is not chained with its own IV, it is chained with the last block of the previous packet, and so on. And here is the vulnerability. Since each packet is separate, a hacker who has control of the browser with a certain JavaScript can forge certain packets, and he would know what would be the IV of his own packet. His IV is going to be the last block of the previously sent packet. And because of that, he can start sending packets with certain words that he knows, and then they would be encrypted with the key that is in the SSL. He does not have access to the key, but he would have access to the encrypted version of his packet. So if I encrypt the word hello with the IV that I already know, and then I look at the packet, and then if I see that portion matches a portion of another packet, I would know that that portion is also hello. So this is used, the beast, if used correctly under certain circumstances, the hacker can reveal, let's say, cookies, can reveal, can get access to passwords, can get access to certain tokens on the HTTPS. Okay. Now, if you remember, how was this vulnerability fixed? It was fixed in the previous version of TLS by creating a unique IV, like the red block here, for every packet. So packets are now, each packet has its own IV, and that's what we call the explicit IV instead of the implicit IV that was in version 1.0. So let's move on to another vulnerability or another attack, and that is the crime and the breach attack. These two attacks affect version 1.0, version 1.1, and version 1.2. And both of these attacks are related to compression. The only difference is the crime attack targets TLS compression. So TLS algorithm has its own way of encrypting, has its own way of doing compression to the data. Okay. So crime exploits this compression, while the breach attack targets the compression of HTTP. So HTTP has its own compression, TLS has its own compression. Crime target the compression of TLS, breach target the compression of HTTP. So even though you can disable TLS compression and then you will eliminate the crime vulnerability, but with HTTP compression, you're still vulnerable to the breach attack. In 1.3, all forms of compression are not used, neither TLS nor HTTP. So the crime one, we're going to look into the crime. Both have the same concept and the same principles. So the crime vulnerability stands for compression ratio info leak made easy, was discovered in 2012 and has its own CVE. It affects 1.0, 1.1, and 1.2. Okay, and we said 1.3 eliminates all compression. That's why it's not vulnerable. And by default, in previous and vulnerable TLS version, client and server can negotiate if they want to have compression or not, if compression is enabled. Let's look at this. The compression algorithm in TLS, the compression algorithm, the way it does, it compresses data or compresses a packet or a stream of data is by checking for repetitive statements. So whenever there are like repetitive statements, it's gonna eliminate all repetitions, and then it will simply put a pointer to the first instance. So if I look at the first box over here, we have session ID equal XYZ123 as a cookie. This is part of the original message. The crime attack also involves the attacker injecting some JavaScript in the browser. So the attacker has some access to the browser. He needs to inject now. He needs to cause the browser to send packets through JavaScript or Java applet. So let's say a hacker now forces the browser to send a packet, and then within the payload of the packet, there is session ID equal, okay, session ID equal. Now, I put here session ID equal A. Now, A is not part of the original session ID. What is part of the original header is the parameter session ID equal. And since session ID is a repetition of the same session ID over there, this portion will be eliminated and a pointer will be replaced. Thus, the packet size is decreased. Now, let's say I keep guessing the first letter, A, B, C, D, blah, 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 until I reach X. Once I reach X, as you can see in the second box, what's gonna happen? Session ID equals X will be eliminated, and thus the message now will be one letter or one byte smaller. The fact that it is one byte smaller means that I have guessed the first letter, which is X, sorry. And then now I keep guessing the second letter, A, B, C, D, E, blah, 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 until I reach Y, as it is in the third box now. Once Y matches the second Y over there, it means my message will look one byte smaller. So every time I get the result on the wire one byte smaller, I can make sure that I have cracked one letter of the session ID. This is the basis of the crime attack or the crime vulnerability. So because of the way compression is done, I keep guessing the secrets, and whenever I guess a letter, my message gets smaller. And this is how I get the hint that I have figured out the letter. And I move to the next one and so on. The breach works exactly the same way, but on HTTP compression instead of TLS compression. The same concept exactly. Let's move to another attack. Also, a very major attack was discovered in 2014 called the POODLE vulnerability or the POODLE attack. The POODLE stands for Padding Oracle on Downgraded Legacy Encryption. Padding Oracle on Downgraded Legacy Encryption. The attack is done in two steps. There are two steps or two phases, and that's why the name is here. We have downgraded, okay, and padding Oracle. So first, I need to downgrade a modern version of TLS to SSL version 3, because the actual attack targets SSL version 3. But SSL version 3 by year 2014 was considered obsolete. However, many websites still enable SSL version 3 by default, even though they are not using it. So they are using, like, let's say TLS 1.1, 1.2. However, SSL version 3 is still enabled. So what the POODLE attack does, it forces the downgrade to SSL version 3. And once SSL version 3 is now used, it then targets and attacks. So the attacker comes in the middle between a client and the server. The clients want to talk in modern TLS version, in a newer TLS version, like let's say 1.2, and then the attacker is in the middle. It tries to drop packets. So it drops the first TLS connection, first time, second time, third time, fourth time. It tries multiple times, dropping the connection. Many web browsers, when the connection is not being initiated or properly established with the server, they switched automatically to SSL version 3. And once SSL version 3 is initiated now with the server, the hacker now can do certain tricks with the way block ciphers encrypt the data, and this has to do with something we call padding. I don't have an image here. Let me see if I can share whiteboard and just give you a little idea about the padding oracle. Okay, I'm sure you can see something here. No. Okay. So we said that any block cipher, if you have like data, something like this, okay, with a bunch of data over here, okay, and let's say it's from here until here, okay. We said that any block cipher, what it does, it makes the data into chunks, we call them blocks, and then it encrypts every block by itself, right? This is what we said, okay. However, the blocks must have a fixed length. Each algorithm has its own block size. When you reach the end, if the last portion of data, if the last block is not filled with all the data, then the algorithm will fill something we call padding. So it will add simply junk, okay, to make it padding, and then at the end it will say what is the length of this padding. Now imagine if the data to be encrypted have exactly is a multiple of block size, so which means the last bit of data or the last byte of data come exactly on the last block, the encryption algorithm will add an entire block just padding. So this will be just padding. What the hacker now does is, let's say in this block I am suspecting a password. There's a password over here. Okay, there's a password over here. If I move this block and I copy it to the padding block and then I send it, the server will only look at the last byte of this padding, and the last byte should be the length of the padding. And if the last byte happens to be exactly the intended length, that means I managed to figure out what is the last byte of this block. If it is not the same, I'm gonna get a padding error. So by playing with this, by playing with copying blocks here and trying to get the last bit of data, what the hacker will do, he can slowly figure out an entire password or an entire cookie by simply playing with the padding. And that's why it's called padding oracle, because from the padding I am doing a divination, I am doing like a guesswork if my bits are correct or not. And this vulnerability only exists in SSL version 3, because in later version this is solved. There is a strict check of the padding. So I downgrade to SSL version 3, and then I use padding as an oracle to guess a certain secret, password or a session cookie, and so on. So let's move on now to another vulnerability, and that is the drown vulnerability. The drown vulnerability was discovered 4 years ago in 2016. It's called decrypting RSA using obsolete and weakened encryption. Drown. Decrypting RSA using obsolete and weakened encryption. If the POODLE attacks SSL version 3 by downgrading TLS to SSL version 3, the drown attacks TLS using SSL version 2, meaning the following. If a web server supports TLS and at the same time it has SSL version 2 enabled, okay, even though it's not using it by default, it's still enabled, okay, what the hacker now can do is, by doing some work with SSL version 2, it can extract enough information to reveal the secret of a TLS communication. This is exactly what it does. So if the victim server uses RSA key, okay, or RSA certificate for both SSL version 2 and TLS, then the hacker can use SSL version 2 characteristics to decrypt TLS communication or TLS session. And the way it's done is the following. It's much complicated than this, but in order to decrypt TLS session, the attacker needs to capture 1,000, minimum of 1,000 TLS sessions using RSA key exchange, and then it needs to make 40,000 SSL version 2 connections to the victim server, and these 40,000 SSL version 2 will reveal a lot of information that will be used to break the TLS session. And then with this information, you will do 2 to the power 50 symmetric encryption operations. And by doing these with mathematical crypto analysis, you can get the secret key of the TLS session and decrypt it. There is a proof of concept available in GitHub, and this is the link of it. And the details about this attack has been given in the paper called Drown, Breaking TLS Using SSL Version 2 white paper. Finally, there are less common attacks and vulnerabilities for TLS, and these are the Lucky 13 and the Logjam. Okay, just quickly, Lucky 13 was discovered in 2013, and it affects mostly SSL and TLS versions. And what it targets, basically, it targets symmetric encryption algorithm that works in a block ciphers. Block ciphers have a lot of vulnerabilities, as we have seen in the in the Beast and in the POODLE. And Lucky also exploit the block cipher. And one of the major features of TLS version 1.3 was the complete elimination of the use of CBC, or chaining block ciphers mode, and they substituted this by using something we call counter mode. What counter mode does is it switches block ciphers to stream ciphers. AES, for example, we know that AES is one of the strongest encryption algorithms nowadays. It works in block ciphers. However, in order to be secure in TLS, they don't use it as a block cipher. They use it in a counter mode cipher, which replaces it, or it turns the block cipher into a stream cipher. So it behaves like a stream cipher. Logjam is another attack, another vulnerability discovered in 2015, and the target Diffie-Hellman cipher. Diffie-Hellman is an algorithm for key exchange. It's a way to generate secret keys in such a way that the key itself is not transferred on the wire, even not transferred encrypted. So there is no transference of the key at all. However, old version of Diffie-Hellman ciphers have a limitation. We call them USA export grade limitation. In the past, more than 15 years ago, the US government has placed some limitation on any encryption algorithm to be used outside the states. And those limitations have weakened a lot of encryption algorithms. So Diffie-Hellman, instead of using like a large key size, a key of larger than 1024 bits, has been restricted to less than 512 bits. And the logjam exploited Diffie-Hellman ciphers that have this limitation. Okay, so we talked about the protocols, the background, and the history of protocols. Then we moved on to the vulnerabilities. Okay, we talked about the POODLE, the Beast, the crime, the logjam, and some others. Let's talk about the cipher suites. You're gonna encounter cipher suites a lot when you do your assessment in any SSL auditing or SSL assessment. However, before we go into the cipher suites, I'm gonna give you like 5 minutes break just to stretch your legs, to have a cup of coffee, or to walk around. Okay, I also have my own break. So we're gonna have 5 minutes break, and then we're gonna continue with the cipher suite and the rest of presentation. All right, guys, I think we're done with the 5 minutes break. We can now continue our workshop or our webinar. So we stopped at the Cypher suites. A Cypher suite is a package, is a bundle of encryption algorithm. Not only encryption algorithm, sorry, of different cryptographic algorithm. It contains the following items, mainly the following 5 items. It contains authentication algorithm, and this is like asymmetric encryption, something like RSA or DSA. It also contains a key exchange algorithm, and a typical algorithm for key exchange is Diffie-Hellman, and there are different types of Diffie-Hellman, like Diffie-Hellman with elliptic curves, Diffie-Hellman that is ephemeral, anonymous Diffie-Hellman, and so on. Bulk encryption algorithm, and this is mainly symmetric encryption algorithm, something like DES, the old DES, triple DES, or the modern AES encryption algorithm. It includes key length, okay, the key length for the symmetric algorithm. For example, AES, whether it's 128 or something else. And then it includes a hashing algorithm used as message authentication code that it provides integrity as well as authentication in combination with the asymmetric encryption. Let's look at an example here. The first one, DH-RSA-AES256, SHA-256. What this is a cipher now, a cipher suite. Okay. The first part, the DH, denotes the key exchange algorithm, the Diffie-Hellman exchange algorithm. Second part, RSA, denotes the public key algorithm used for authentication, and it is the algorithm of the public key within the certificate. And then the third part over here is the symmetric encryption algorithm, AES, and the key length is 256. And then finally, we have the message authentication code, and that is the SHA-256. So this entire thing we call a cipher suite. The same thing here in the second example. I'm gonna skip the second example, third example, and the fourth example because a little bit they are redundant, similar to the first one, but simply different algorithms, and jump into what makes a good algorithm versus a bad algorithm. And if there is something I want you to take about to take away from the cipher suites, it is the following principles. Any any cipher suite that contains RC4 encryption algorithm is a bad algorithm. It should never be used, and if you encounter it in any server during your assessment, it should be directly, it should raise a red flag and report it immediately. RC4 is an outdated algorithm. It's insecure. It has a lot of problems. It should never be used. If you encounter DES or triple DES encryption algorithm in any cipher, it's also a red flag. Do not use it. If you see MD5 hashing algorithm, again, MD5 is totally insecure. shouldn't be used, should be disabled at all costs. No MD5. Always use SHA-1 or SHA-2. Never accept any ciphers that has no encryption algorithm or no authentication. Some ciphers have null encryption or null key exchange or null authentication. Disregard them. Disregard every cipher that has export grade limitations, as I described. An export grade limitation has very weak key length, whether it's public asymmetric encryption or symmetric cipher. Any cipher suite that has export in it, the word export, it means it is limited and should be disregarded. If you are using the O-Saft tool, which I'm going to explain in a while, using the command plus list is going to give you a list of ciphers, in general, a table of all available cipher lists, and it will tell you which one is weak and which one is strong. As you can see here in this image, you have got the weak and the high security and medium security and weak or low security. So you can use this as a reference guide when you are doing your assessment. Let's now move to another important topic, which is SSL and TLS hijacking. SSL and TLS, the very purpose and the very reason why we have them is to encrypt traffic. SSL hijacking defeats this very purpose. With SSL hijacking, the attacking can check the very data itself that you are supposed to encrypt with SSL and TLS. And there are two ways to do SSL hijacking. The first one is through forging a fake certificate. So the attacker will send a fake certificate to the client. The client will see an invalid certificate warning, okay? And if the victim accepts the invalid warning, he's gonna fall into the trap, and the attacker can now view the traffic. He can access the traffic and can see it in a clear text. The other method of doing SSL hijacking is called SSL stripping. And the SSL stripping exploits one functionality of a browser, and that is the redirect mechanism. We will look into both of them right now. So, with the certificate forgery method, the attacker sits in between as a man in the middle between the web server and the client, okay, as you can see here. And then it acts as a router, so everything can come and go, come and go, come and go. And once the attacker sees a certificate, a valid certificate coming from the server, from the web server, distant to the client, the attacker will stop it. It won't let it pass. It will stop it. It will stop it here, and then the attacker will forge his own fake certificate to the client. And the attacker, of course, he has the private key of that certificate. So the client now receives the warning. If he says accept the warning, accept the invalid, what's gonna happen? The client now will initiate an SSL connection with the attacker based on this fake certificate, and the attacker will have a valid connection, a connection using the valid certificate with the web server. So when the communication happens, a message comes encrypted from the web server to the attacker decrypts it, he has access to it, and then encrypted using the key with the client and send it to the client. Neither the server nor the client knows they are being hijacked. Both ends, they think they are still talking to each other directly, while the attacker is in between viewing everything. One tool that does this attack is called EtherCap. Okay, it comes in Kali, and it can achieve man in the middle, and it can forge a fake certificate, and then it does all of this routing and decrypting automatically for you, and then you will have access to the decrypted data. One way to prevent certificate forgery is a technique called certificate pinning. Certificate pinning. What is certificate pinning? Certificate pinning is when the client accesses a web server for the first time, the server responds with a header called public key pins, and then it will instruct the web browser that from now on, it should use a specific certificate. So the web browser now will catch the certificate, and for any future communication with that particular server, the web browser only accept this certificate, a certificate that is pinned. So if a hacker comes in between and forges his own fake certificate, the browser will reject it automatically because the legitimate certificate is pinned. So you might ask yourself now, okay, I have secured all subsequent connection, but what about the first time? So if the victim clears the cache of his web browser, the pinned certificate will be deleted. So the first attempt is always vulnerable to a forgery. So the way they solved it is, we're gonna talk about the way later on in the HSTS. Another problem of the certificate pinning is, let's say you have pinned a certificate, later on the server changes its own certificate for some reasons. Now, the client will not be able to talk to the legitimate server because the pinned certificate is different than the new certificate. So it causes a lot of problems. That's why certificate pinning is now deprecated. It's not used anymore. And they switch to the HSTS. Another method of hijacking hijacking SSL at TLS is called SSL stripping. The main difference between SSL stripping and certificate forgery is the client now will not get a warning, will not get this invalid certificate warning, blah, blah, blah. It becomes totally seamless. SSL stripping exploits the following fact. When users access a certain website, let's say they type in their browser axontechnologies.com. They did not type HTTPS, nor they typed HTTP. They simply type axontechnologies.com. The web browser automatically is going to connect over HTTP, not HTTPS. It's going to connect over HTTP. The server will send something we call redirect, okay, to HTTPS. Then the browser connects to the HTTPS. A guy called Moxie, Marlin Spike, came along and invented a tool called SSL strip and a technique that works like this. So he said, if a client first connects to HTTP and then the server sends the redirect before the communication takes place over HTTPS, he can come in between and hijack the redirect. So his tool does the following. He will monitor the first HTTP request. He will let it pass as he is man in the middle. When the redirect comes, the redirect says redirect from HTTP to HTTPS. However, he will change it to redirect to HTTP. So he will strip the S from the HTTPS, and then the client will receive redirect to HTTP instead to HTTPS. The client now tries to connect to HTTP instead to HTTPS, but the SSL strip machine will stop the communication and have its own HTTPS established with the server, and then anything that comes from the server will be decrypted, and then send over HTTP to the client, and then the other way around. So in here with SSL strip, the hacker can access the traffic, can see everything, and the client will not get a certificate warning. However, in the web browser, he will see only HTTP. The way they solve this problem is by creating something, a technology or a technique called strict transport security. Strict transport security, it fixes the problem of the certificate pinning, number one, and it solves the redirect issues. So when the client connects to the server for the first time, the server responds in its header with strict transport security. And then the client now will cache in its browser cache that in any future access, I need always to connect through HTTPS, and it will never connect through HTTP. So there is no more redirect. And also, it will only accept valid and trusted certificate. So it will eliminate the possibility of exploiting and hijacking redirect. It will also eliminate the possibility of certificate forgery. So if a certificate is forged in the middle, not only there will not be warning, and the user has no option to bypass the warning, it will simply cut off the communication. You are simply not allowed to connect. However, there is still a window of attack, which is the first time. As I said, because the first time you connect, the browser has no idea about this header, about the HSTS. It has to be cached after the first time to be useful. But for the first time, there is no HSTS. The web browser is still vulnerable. Also, if you access and you have the HSTS header and is stored, but then after some time, if the victim clears the cache, it's going to be deleted. So for the first time or every time after you clear the cache, there is a window of vulnerability here. So how to eliminate this window of vulnerability of the first time? They said, and actually Google said, and this is something invented by Google now, Google invented something we call HSTS preload list. So Google made a list now, and it puts its first domain. For the first time, it puts its domain, and then it increased it later on. And then it made this list embedded in Google Chrome. So when a user now tries to access google.com, the Google Chrome browser, it checks the list and will see that Google is embedded in this list, and it will go, even for the first time, it will go with a strict security, which means to HTTPS and with a valid certificate. And if by any chance it receives an invalid certificate, it will drop the connection, and there is no way to bypass the warning. And then over time, the list is enlarged, and more domains are added to the list. Now you have got almost all well-known websites like Facebook, Instagram, WhatsApp, all those LinkedIn and so on are added to the list, and there are hundreds of domains inside this list. And also this list is not only now embedded in Google Chrome, it's embedded also in Firefox, embedded in Internet Explorer, okay? And any domain has the option to join this list. So if you have a website and you would like to be added to this list, you simply go to hstspreload.org and then check the requirements. You have to have a valid certificate. You have to configure the HSTS header in your web server in Apache or IIS, and then you have to submit your domain. It's free of charge, and then after a while, they checked your domain, and if you meet all the requirements, they will add you to the list, and then your website becomes immune to any form of SSL hijacking. Let's talk about now our favorite tool for auditing and assessing SSL. As I said, there are different tools, multiple tools. We're going to look at some of them at the end, just a list for your reference if you want to check. But the primary tool, one of those tools which I like so much and I use it very often, is called the O-Saft tool. Stands for OWASP SSL Advanced Forensic Tool, and sometimes it's also called OWASP SSL Audit for Testers tool. So it does a comprehensive assessment of the protocols, the protocol versions, the vulnerabilities. It checks the cipher suites. It checks the HSTS header. It checks the perfect forward secrecy. It checks for the existence of compression, renegotiation, and so many other things I have talked about. And then it gives you a full report, or you can have a quick assessment, or you can have an assessment of a particular aspect of the protocols, or you can have a full assessment, so you can control what type of assessment you want to have. Let's look at a few examples here, or common ways of running the tool. Here I'm running. So the way you can run this tool is you specify the name, the O-Saft, O-Saft, and then you give it the command. There are different built-in commands. One common command is the protocols. Each command must be prefixed with the plus sign. So plus protocols, it means check the protocols, the SSL protocols of the domain HTTPS mydomain.tld. So you give it something like axontechnologies.com or whatever your domain you have, whatever domain you have. So protocols will check the SSL and TLS protocol versions, and then it will give you a report. Here, for example, I'm running it against a certain website and it's telling me target does not support SSL version 2. Yes, it means it does not support SSL version 2. It does not support version 3, which is good. However, SSL supports version TLS version 1. No. Supports TLS 1.1. No. Supports 1.2. Yes. So that means it only accepts 1.2 in this example, and 1.3 is not supported. I can check if perfect forward secrecy is enabled or not, or supported or not. I run it with the command plus PFS, and here I have, it has PFS ciphers, but not for all ciphers. So only some ciphers have PFS. We talked about PFS, and we said PFS is good for creating keys every period of time, so that if a key is compromised, it does not compromise the entire communication. Another way is to check if your target domain supports SNI, the server name indication, and we mentioned that SNI is an extension of TLS 1.2, and it enables multiple HTTPS websites having two different certificates running on the same server on the same 443 port. So here I'm running it against Axon Technologies, and what I get here, if I check connection, is not based on SNI. No, which means connection is based on SNI. That means my domain is hosted with others' HTTPS domains on the same system. Another thing, I can test my target domain with HSTS. So if I give it the command plus HSTS, it will do some assessment. If I have HSTS header here, target does not send STS or HSTS in metadata and meta tag. Yes, so it is not supported. HSTS is not supported in this example. So does not send, yes. Does not send STS header, yes. Does not redirect, yes. Redirect without STS, yes. So HSTS is fully not enabled, and all other features of STS are not also enabled. EV, if you can, as you can see here, EV stands for extended validation. I have not talked about the extended validation. When you issue your own certificate, the certificate authority that gives you the certificate can either validate you at the domain level, or it can do something we call extended validation. At the domain level or domain level validation, domain validation, DV, they only check that you own your own domain. So if I'm issuing for axontechnologies.com, the only thing I have to prove to the certificate authority is that I have control over Axon Technologies domain. However, with extended validation, they are going to ask me extra questions, that I own the company, that the company is registered, that my phone is correct, that my address is correct, and so on. So if I want to test if my target domain supports EV, extended validation, what I do, I issue the command plus EV, and all I can see here is domain validation, yes. So in my case, domain validation is actually, it is actually the least level of validation. So it has to be yes. There is no SSL without domain validation. And extended validation, it says no. That means my certificate does not have the extended validation feature. Now, if I want to do a comprehensive assessment of my website, I can issue the command plus check. Plus check will give me a very large report of my assessment of my target website, and with a lot of details. Okay, it's beyond the scope of the webinar to go in every single detail, but I have written here few details. I will go through quickly. It says connection is safe against RC4 attack. So we said RC4 should be eliminated. What is the total number of ciphers? It will tell me if HSTS is enabled. If it checks if Heartbleed extension is enabled, it's one of the TLS extensions, and there is a vulnerability related to it in OpenSSL. It will tell me if the certificate is valid. Yes, target does not accept null ciphers. We said null ciphers contain, they lack some encryption algorithm. Target support ephemeral Diffie-Hellman ciphers. Yes, this is something good. Diffie-Hellman key exchange is good. When it is ephemeral, it means the keys are not static, but they are changing. Certificate is not expired. Yes, which means it's good. Certificate is not root CA. Yes. Certificate chain is validated. It means the entire chain is being validated. Does it support version 1.2 TLS? Yes, it supports 1.2. There is no public key pins. Does it support version 1.1? No, which means this is good. because 1.1 is outdated. Does not support SSL version 3. Yes, this is something good. Certificate is not self-signed. No. And then we have certificate strict extended validation. No, that means it is domain validation. Does not accept RC4. Immune to beast attack. Yes. Redirects to HTTP without HSTS. Yes. It checks for Suite 32 attack, similar to the other attacks we talked about. And then we have the freak attack as well. Target selects strongest cipher. No, this is not something very good. So it does not select the strongest cipher. It selects one that's a little bit weaker, but it's also strong. So two strong ciphers. One is stronger than the other. It does not select the strongest. It selects a strong, but not the strongest. What is the public key size? Fingerprint is not MD5. This is good. It's SHA-1 or SHA-2. Certificate is valid. Yes. No compression. This is also a good thing. Perfect forward secrecies also. They're immune against Heartbleed attack. Yes. Does it support secure renegotiation? Yes. Immune against Lucky 13, against Drown, against POODLE. Yes. Does not accept DES. We said DES ciphers are obsolete. Domain validation. Yes. And others we have talked about. So the last portion of this webinar is related to the OWASP testing guide. Those of you who are familiar with the OWASP is a non-profit organization responsible for web application testing. They have a framework for testing web application and also mobile application. And in their testing guide, there is one section just for SSL and TLS. And this section is, the number of this section is 4.9. So if you go to the testing guideline of OWASP and you go to 4.9, you will see a section on weak cryptography. The first, the first two subsections, the 4.9.1 and 4.9.2, are related to the SSLTLS, while the rest are for different cryptography, not directly related to the SSLTLS. And this is the home page of the project where you can check. Basically, it gives you certain guidelines and the principles, exactly like we talked about in this webinar so far. It says you have to make sure your target domain uses secure renegotiation. Insecure renegotiation should be disabled. You should not use MD5. You should not use RC4 ciphers. You should be protected against the beast attack and the crime attack. So if you have 1.2 or 1.3, you are immune. You should support perfect forward secrecy. Finally, the testing guidelines from OWASP gives you another set of tools in addition to the O-Saft we talked about, and these tools are Nmap. You can use Nmap to do some SSL assessment. There is a tool called Test SSL Server, and there is the SSL YZE and Test SSL and Breacher. So I'm done with this webinar. This is the end of our webinar talking about SSL auditing and SSL assessment. Hope you guys had great benefit and great value of it. If any of you, we have like 10 minutes before the end. If anyone has any question, I can give you the mic to ask any question. You are most welcome, whether by voice or you can ask in chat, and then we'll be happy to answer you. Thank you, guys. Thank you. Looks like nobody has any questions. Thank you for joining, everybody. Really appreciate it. Hope you had a good evening. And did the session was the session recorded? Yes, I think the platform record this session automatically. We're gonna check it and see how we can probably give you links by email to the recorded session, and maybe we can even publish it publicly as well. Thank you, thank you. You are most welcome for everybody. Hope we catch up and see you in future webinars as well. If you have any questions, you can send me by email aws@axontechnologies.com. AWS, I'm gonna write here my email address on the chat, axontechnologies.com. So thank you guys again, and see you in future webinars. Bye bye.